Got it. So I guess I'll say hello. I'm Jeff Stuecheli. I live down in Austin, Texas, and we do hardware design for power processors, so architecture. I've been doing power my whole professional career. My previous job was delivering pizzas at Pizza Hut, but I've been at IBM since, I guess, the mid-90s, so I've been working on power the whole time. So today, this is a Power Hardware Roadmap, Accelerating Compute with Heterogeneous Composability. That was just kind of a fun thing to call it, but fundamentally what we're interested in is kind of this concept of composable hardware systems. So if we kind of look at what that means, so plug this in. Let's see if this works. Yeah. So what do we want to do with composable systems? Historically, let's say even in a traditional data center, you might find a processor with some network on it, but these are non-heterogeneous, homogeneous computing systems where just everything ran as C code in the processor. And as I'm sure everybody's pretty aware, we have a slowing of transistor frequencies, transistor densities, this whole slowing of Moore's law on the horizon, and so we've transitioned to more acceleration-based solutions. So you have Xilinx acceleration, which we just heard about, which is the ability to highly customize a workload, an algorithm inside of an FPGA. You have GPUs that are really a GPU, I should say, which is really a different kind of CPU in a lot of senses. It's a bunch of really weak, really efficient, large numbers of threads. And so some workloads run well on highly parallel applications, and those can exploit things like GPUs. But fundamentally, I guess what we see going forward is that when somebody's trying to deploy an application, they're going to have a menu of these different types of devices to attach to their processor. Perhaps combinations of GPUs and FPGAs, right? The FPGA could do some inferencing, the GPU might do some video analytics, I don't know. There's also an opportunity for other ASICs. It's not that I don't like our NVIDIA partners in open power, but it seems like there's probably other types of acceleration devices in the entire world that will benefit systems. And so I see us needing to build other types of accelerators beyond what we have today, in the next 10 or 20 years. Beyond that, we've got memory, and memory is also changing. So I'm kind of giving my entire presentation right now, but fundamentally what this talk about is, okay, what do we see needing to do into the future with this heterogeneous kind of system architecture? So Power 9, I guess I should toot our horn a little bit. We view ourselves as the premier accelerator platform today. So if you look at what you can go buy off the market today, we support NVLink 2.0 to connect high bandwidth interfaces to GPUs. We have PCIe Gen 4. You can run CAPI components on top of that, which is some of the stuff we have with our Mellanox partnership, is address translation utilizing some of the CAPI solutions. Beyond that, we have open CAPI capabilities where we can run high frequency differential signaling out to FPGAs or other devices potentially. Memory is one thing we've been spending a lot of time looking at. So we have kind of the latest, greatest PCIe, the latest, greatest 25 differential signaling that we can use for a variety of different purposes. This is very much a composable system. It's also very much the most sophisticated thing you can get out there today. It's probably worth, since the question came up a little while ago, I think it's an interesting discussion around PCIe Gen 4, which runs at 16 gigabit, or gigahertz, I don't know which one is the best word to use, but it runs at 16. The open CAPI stuff runs at 25. So 25, isn't really that much more than 16, if you kind of stand back far enough. But what you have to keep in mind, and this is an interesting question for the overall world here, which is PCIe, you can plug in a Gen 1 PCIe card into it. You can plug in a Gen 2. You can plug in back-level devices. It's extremely flexible. But because of that, the PHYs have to have multiple PLLs to be able to run at different frequencies. The multiplier for Gen 1 is different than the multiplier for Gen 4. So there's really a lot of overhead in this PHY here to be PCIe and to be as flexible as PCIe is. The 25 gig PHY, on the other hand, it's about half the power cost to do this 25 gig than it is PCIe Gen 4. So it's kind of it's a compromise we have to think about. We want to have, if I'm off building a host processor and I'm going to attach a bunch of, purpose-built, I know I'm going to put a high bandwidth GPU or a high bandwidth network onto it. Is it really a good idea for me to put those on a Gen 5 or Gen 6 PCIe that has all the baggage of Gen 1, Gen 2 built in? Or should we build a new PCIe that's just capable of doing the high frequency sorts, which is really what we've done with OpenCAPI. So that's, just a little bit of a soapbox here. Right now, everything in PCIe Gen 5 and CXL offer, with deprecated performance, the ability to plug in old devices. But because that deprecated performance is offered, we have quite a bit of overhead in how many lanes we can efficiently put on a processor. And it's a bigger problem for the host than it is necessarily the device. Right? We're trying to put hundreds of lanes of devices off of our host to connect lots of GPUs and lots of devices. So we have to pay that tax more so than like a single GPU that may only have one by 16 port on it. So, and that's absolutely what, if you look at what NVLink is on the NVIDIA side, they don't have backward compatibility between different generations of GPUs. It's not like you can take a Volta and hook it up to a Pascal, right? It's optimized around talking to themselves at high bandwidth. And so we got to think about how we're going to address that in the future. Right now I don't see anything other than OpenCAPI that's doing optimized frequency, but I'm a little suspicious about how well Gen 6 is going to work because of the difficulties of attaching the old stuff to it. But right now there is no proposal for anything in the CXL PCIe space to really get around this problem. So let's talk cores for a second. This is a lot of the work I do at IBM is working on making high-performance cores, so I definitely got to put it in the slide. The key message here is that if we offloaded all of our highly parallel work to accelerators, what we're left with is the stuff that was hard to write for accelerators, which is going to be piles of junk code, right? Code that's serial in nature, not necessarily easily optimized. So that means cores in this composable heterogeneous ecosystem need to be able to run, crappy code well, right? So high clock rates, potentially investing a lot in, things to run Python code or branchy code well, lots of control dependencies. And so that's what we did. We bit off kind of a big bite here between Power 8 and Power 9. We redesigned our whole core microarchitecture targeting these types of future systems. And we're continuing to do so. We're continuing to push our core design, but I don't have too much to talk about that other than that is definitely important, is the ability to run code in that space. So I put accelerators next for a reason. I typically do memory next, but you'll kind of see why I mentioned accelerators next at the end of it. So this is a chart from the now retired Bruce Weil. I don't know if you guys ever saw him. But it's worth showing. I don't know necessarily how much time we want to spend on this, but there's a lot of different things you might want to do with acceleration infrastructure. You can be accelerating data that comes in from video feed, right, pre-processing it. You could be doing batch acceleration, right? There's all kinds of different application-specific capabilities which you want to accomplish. So if you look at that Xilinx card back there, it's got the SPF connectors, SPF whatever, I forgot what they're called. It's got connectors to talk to network. It's got connectors to talk to other FPGAs. But you're definitely having to do processing, talking to the outside world. There are just straight up accelerate cases though. If you look at what we do with GPUs, that's this one here, right? There's not an outside world connection going into a GPU. It's a straight offload example. That said, it's also heavily dependent upon memory being tacked onto the accelerator as well to be efficient. So, is there any thoughts here? Does anybody want to say anything? The discussion group. All right, we'll keep going. So here is what we have with OpenCAPI, which is we started back in CAPI 1.0 in the Power 8 time frame, which was very much focused around taking a PCIe device and building protocol on top of that to add coherence, and also to be able to do things with just programmed addresses. That's probably one of the bigger items that we built in there, which is you don't want to have to go through device drivers to try and figure out how to traverse a pointer. This is kind of similar to ATS on PCIe, but this ATS isn't a widely adopted feature, or it certainly wasn't back then. And so we built kind of our ATS cache coherent thing and called that CAPI. CAPI 2 was essentially something we did in Power 9. This is used by PCIe devices to get access to some of those address translation features, but it's become a little bit less prominent as an accelerator architecture because we have Open CAPI in Power 9 as well, which is taking those 25 gig links and building a very latency optimized protocol to talk between accelerators and the host memory. So that's what you see in CAPI, Open CAPI 3.0. Keep in mind it doesn't have much in the way of coherence here because we kind of did this fairly quickly based around more of an accelerator DMA based approach rather than the thing we have over here, which is more coherently minded. So now the next versions of CAPI have coherence in them based around virtual addresses. That's really what you see in Open CAPI 4.0. The other thing we've built here, which is called Open CAPI 3.0 or 3.1, it's a little bit unfortunate in some ways though, because what we like to put, we'll get to this in a second, but memory devices today, DDR memory devices, the DDR5 protocol is highly inefficient from an area perspective, area power perspective. I said that PCIe was half as good as our optimized PHY. DDR is like 1/6, right? So there's a 6x improvement in the ability for us to drive bandwidth onto the chip moving from DDR signaling to Open CAPI-based signaling. So however bad I kind of said PCI is, DDR is dramatically worse. So what we did was we got all these high efficiency signaling technologies. Let's figure out let's put DDR on those interfaces. And what that meant though is DDR attached for main memory has extreme latency requirements. It doesn't really need to master commands or have cache coherence though. So we built a subset and called that Open CAPI 3.1. The thing that's been a little bit unfortunate about that in some ways is we went to JEDEC, this is a JEDEC standard, and calling it Open CAPI made people think that it was related to accelerator attach and had baggage or issues. They were thinking this is Open CAPI, and we even had places. I guess I can say this because it's a discussion group. People from other companies who were Gen Z fans or C6 fans were like, well, I don't want Open CAPI to be the memory standard because then they'll win in the I/O wars, right? So there was definitely some of that going on, where people didn't necessarily take it as seriously as I think they should because it was called Open CAPI. So now we don't call it Open CAPI anymore, we just say OMI, because it's Open Memory Interface. It doesn't have a lot of the Open CAPI accelerator things in there, but what it does have is an ability to attach DRAM with low latency and low overhead. So now it's OMI, Open Memory Interface, and then we do have standardization activities in JEDEC, and this essentially lets you put buku bandwidth into your devices, right, that you can't do with the DDR-based solution today. CXL, we're on the board of directors as well. Steve Fields is our representative there. I'm in the several of the work groups as our voting member, so we have people working on CXL. If there's CXL devices out there, the whole goal in Open CAPI to a large degree was to make PCIe, PCIe wasn't doing it for us with Gen 3 in particular, even Gen 4. If the industry is going to get behind a standard, we want to be involved in that as well, right? A big part of our differentiation on the second slide was having leadership PCIe capabilities with PCIe Gen 4. So we're excited about this, and that if there's going to be lots of devices, we want to have a broader set of devices and ecosystem. Like I said, some of the skepticism or some of the concerns I have in this are being on PCIe means you have a bit of baggage by being tied to PCIe. And so we'll see how this goes, right? As far as can it stay like a tight host processor interconnect, Or is everybody going to want to put switches in the interconnect and make it as much as PCIe is? And if you make it do everything PCIe can do, then you bring in all the limitations that PCIe had. And so it's, you even heard that in the Xilinx comment, which is, we may still want C6 Xilinx did because CXL isn't necessarily doing what we want to accomplish. So, but we certainly support the development of open standards, so we will continue to do so. And also, if you think about it, what are we trying to accomplish IBM with regards to power and open power? Is we're trying to be able to build high capability systems. So we're looking for bottlenecks, I should say. And one of the bottlenecks we saw back in Power 8 and Power 9 was the PCIe bus didn't have any bandwidth, right? It was an inadequate amount of bandwidth. So that was a place we innovated, right? But looking forward, with Gen 5 PCIe and Gen 6 PCIe has been on a massive curve, so maybe that's less of a problem going into the future, right? I mean, this was a proprietary, non-open standard. If PCIe really gets to the speeds Gen 6 is purporting, then in some senses, that's not a problem anymore. But what is a problem is DDR memory. If you're going to try and drive Gen 6 bandwidth into a host with any number of lanes, you're going to run out of memory bandwidth pretty quick with any reasonable DDR solution. So what we have been doing is switching to a differential signaling, which gives us, these are peak to peak. We can go from about 170 peak today to 409 peak DRAM bandwidth. This is OMI plus DDR4. I mean, it is still native DDR devices on the end. And that can support these high bandwidth devices. And we don't only have the accelerators, we've got network, we've got the processor itself, potentially formatting data as it comes in from disk, or I shouldn't say disk anymore, should I? Storage, network, etc. The memory bandwidth is a problem here. And I think this is, I didn't put the one other slide in here that maybe I could have, which is, there is HBM memory. But HBM memory capacity is a bit, it's low, right? If I've got, 2 GPUs with 32, 64 gigs of HBM memory, I kind of need my host to be able to have more capacity than the devices I'm attached to, because it's kind of the pool of memory that the OS and everybody's using. So while there are high bandwidth options with HBM, there are not high bandwidth, high capacity options with HBM. They also have a lot of cost associated with them. So we see the host as wanting to stay on more traditional memory technologies, but it needs a lot more bandwidth than you can get with a DDR solution. So that's that section. Oh, actually, no, I'm starting on memory now. I'm getting too far ahead of myself. So one of the things we did here was we have built buffered memory solutions with differential interfaces really pretty much as long as I've worked at IBM. So that's what we have in this picture on the upper left here. So we sell Power 9 systems today, same as our Power 8 systems and before that, which essentially takes, instead of doing that DDR protocol that has a very physically area or edge perimeter expensive PHY, we don't put that on the processor, we put that out on these buffer chips. And so if you're trying to get a lot of perimeter area, a lot of small chips enables you to have more perimeter than one big chip, right? That's kind of just basic geometry. So we do high-speed signaling, which is much more area efficient on the processor chip, out to these buffer chips. We fly through the buffer chips and then go access DRAM. The only problem we had with this buffer here is it was expensive and designed around big, expensive enterprise servers. So when we did Power 9, this was really our only area, cost-optimized solution was traditional DDR4. So what we're doing going forward, though, is we basically took all of our experiences in building these beefy buffer chips, and we built through JEDEC and through partners in Open Power a lightweight buffer chip to let us get kind of the bandwidth capabilities of this with the density and cost attributes of this type of form factor. So think of this as an alternative to like an LR buffer on a DRAM device, but it talks differential signaling to the processor. So what are all the different memory paradigms associated with that? The one I've just been talking about is DDR. But one of the problems with DDR memory is it has a fixed latency. It's not very flexible in what type of memory device is behind it. So you do a activate and a cast or whatever, and you get data back in 15 cycles. You can't have, non-deterministic latency. You can't have high latency events. And so DDR as an interface doesn't allow for that. But what we've built with these new interfaces, agnostic interfaces, is you do a read operation, you put a tag with it, and the read data can come back out of order. Right? So read data can come back out of order. Write data has explicit commits. As opposed to DDR, you send the write, if you don't get an error, then it's done. With this device, you send a write, and you get an explicit commit back from the device. So what that lets you do things like memory persistence in a much more natural way compared to a DDR memory persistent device. And so you can think about different paradigms here. You can put a bunch of DDR on the interface, or you can put storage class memory directly on the interface. One thing we've been pretty interested in lately is really a hybrid solution, right, where there's DDR memory that's a cache of storage class memory living behind it. And this makes it to where you can, you don't have to waste a memory slot, so to speak, to put your storage class memory. You can still have all the bandwidth, all your slots, and you don't have to have software explicitly paging memory between your DDR and your storage class memory. If you're trying to do some kind of runtime optimized environment, you can do that through a hardware-only solution where you basically plug in a card and it magically looks like more memory because it automatically pages things into it. So that's something we've been interested in building. Other important thing here is, what are the memory options for a host today? You really have three fundamental options. You've got traditional DDR memory, where the flexibility and capacity is there. You can put in DDR4, small memory devices. You can get DIMMs with great capacity with load-reduced buffers, 3D stacking. These do get kind of horrifically expensive. But that said, you don't really have that much flexibility. The bandwidth is fairly fixed. You can grow capacity at a cost adder. So with the OMI solution here, you can do a DDR-based memory device. You could also build a GDDR-based device or an LPDDR device. So even just keeping within DRAM technology, you can build different variations on capacity versus bandwidth, which is something you can't do with a DDR4 interface. You can't go and plug it. You can't build a processor that talks DDR and also talks GDDR. The frequencies are totally different. The PHYs are totally different. But since you disassociated the phi, right? This is like this whole decomposition thing. You move the phi to the buffer. This stays the same, and now you can build different capacity and bandwidth optimized memory technologies for the same DIMM slot, and that could be phase change memory as well. The third technology you have is HBM, which HBM does provide extreme bandwidth, but it suffers from flexibility, right? The customer can't go and plug in different memory capacities other than what you stick on the module when you manufacture it. And there's really just not a lot of capacity here. I put 32 here. Certainly there'll be taller stacks out there in the future, and you could put a whole pile of HBM on your module, but there's just a lot of complexity here. One thing it does give you, though, is density, right? And a lot of bandwidth in a small form factor. So for like the GPU use case where 32, 16 gigs is reasonable and they need tons of bandwidth, partially because of their programming model, right? If you have a whole lot of little threads, a lot of their performance comes from being able to overlap misses to memory, so you kind of inherently drove a lot of bandwidth in a GPU infrastructure. So you can almost think about the HBM on a GPU as a cache of its working set, right? Because it's kind of what you're dealing with. So it certainly makes sense depending on what you're trying to build, but it does remove a lot of flexibility in what you can deploy in your systems. So here's a picture just so you can see kind of how we've gone. This was a Centaur DIMM, which fits in a 4U box, right? This thing's pretty tall. We do have 2U versions of it as well. Actually, that's a 2U card now that I think about it. The 4U card is like, this tall. It's nice because you can put a tremendous amount of capacity. We could put like 64 terabytes of RAM in one box, but it's not necessarily a cost-effective dense solution. This is the size of a JEDEC DIMM. So essentially what we have with this OMI DDIMM is something that's about half the size of a JEDEC DIMM with the same amount of memory bandwidth capability on it. So this is one channel of DDR, this is one channel of DDR. So our box designs can basically put two of these DIMMs in the same space you would have one of those. That gives us basically 2x the amount of memory bandwidth into a processor as you could. We're also able to run these at a little higher frequency, but that's going to be very dependent on the exact compare point. But today we run these at 2666. This will be running at 32 gig, or not 32 gig. That'd be awesome. 3200. So this is 3.2 gig. And basically what we do is we just have a synchronous interface here. We multiply it by 8, and then you get your 25 gig frequency, 25.6 for counting megahertz. Right, so we got the little DIMM I just showed you for our enterprise systems where we do still need all that reliability because we're still building computers for banks and Costco and Apple. We still need to have redundant memory devices, redundant voltage regulation. So in that same connector, we're able to build these enterprise DIMMs for IBM systems. So we didn't really compromise in that regard. We just built a buffer that could be used in a low-end system, but then we built the other components to make our enterprise class systems as well. So this is, I like to show other people here. I guess there's nobody from Rambus here, or is there anybody? We've worked a bit with some of the Rambus people, at least in the past, and they've been building prototype devices on OpenCAPI for some of these hybrid memory solutions. And that's kind of what we want maybe some of the people in this audience can help people with is we've got these systems, we certainly can make, given the right reasoning, we can give early access to systems for people to try out new types of technologies and prototype things. And this is more of an example of somebody doing so over at Rambus. I think he may not be at Rambus anymore, so that's okay. So that's really what I have to talk about. Talked pretty fast, but maybe we got time for questions here. I think I started early too.